So let's look at one like number 46. I've drawn a graph similar to the one that is in that problem. And this is again the graph of g. Now we're going to define a new function h of x to be the integral from 0 to x of this function g. Okay, and so again, this h of x is sort of an area accumulation function, signed area, as we go from 0 to x. Okay, now from this, we're going to answer hopefully questions about the location of where h is doing things like increasing, decreasing, where it has local max mins, where it's concave up and concave down, and where it has inflection points. Now be careful, you're not looking at this graph as, where it's increasing. In other words, you don't want to say, hey, it looks like it's increasing as we go from x equal 4, it's going up, up, up until x equal 8, increasing from the interval 4 to 8. No, that's where g is increasing. I want to know where h is increasing. So you say, how do we get h, or do we sketch a graph? What do we do? No, we don't need to do that. What we need to do is use what we know from Calculus 1. So let's review real quick what we know from Calculus 1. We know from Calculus 1 that if a function is differentiable on an open interval, if the derivative is positive on that interval, then the function's increasing. If the derivative is 0 on that interval, then the function's constant. In other words, it's just a horizontal line. If the derivative is less than 0, then we know the function's decreasing. So you should remember that from Calculus 1. We also have a test to determine whether we have a local max or min at critical points. If you remember, critical points are where the derivative is 0 or undefined. So if we have a sign change in the derivative at a critical point from positive to negative, what's that mean? Positive means, of course, that we were what? We were increasing. Negative means then now we're decreasing. So going up, 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 and then going down, down, down. What do we have? We have a local maximum at that point. Similarly, if the derivative changes sign from negative to positive at x equal a critical point, then we have a local minimum. So that's how we can test that. Now, concavity, right, has to do with the curvature. A function is said to be concave up on an interval. The definition really is where the derivative is increasing. It doesn't mean the derivative is positive, but where the derivative is increasing. Okay, that's the definition. It's where the second derivative would be positive then. But the first derivative is increasing. If I look at the slope, let this pen just be the tangent line that just touches the graph here. As we move from left to right, the slope of our line is getting more increasing, right? It's negative here, but it's getting less negative. So maybe it's -6 here, -5, -4, -3, -2, -1, and then right there at the bottom, right, we're going to have a horizontal tangent line derivative of 0, and then +1, 2, 3, and so on. So we're increasing, derivative is increasing as I move from left to right, and that gives us the shape of concave up for the graph of the function. So the function's derivative is increasing. It looks like this. Notice that we can have the derivative increasing, but negative on this half, so that the function's decreasing, but concave up, and then we can be increasing concave up. Here, concave downward is when the derivative is decreasing, right? Derivative is decreasing, slope is decreasing as we move from left to right. Again, you can be increasing concave down, this little segment, or decreasing concave down. So keep in mind, again, increasing does not mean positive, and decreasing does not mean negative. They're not the same thing, although we do have a relationship, right, that a function is increasing when its derivative is positive. Okay, and a function is concave up when its derivative is increasing. So you've got to have these relationships down from Calculus 1 to be able to answer this question. Now you say, well, what is the derivative of our function h? Well, that's where our fundamental theorem of calculus part 2 comes in, right? The derivative with respect to x of the integral from a to x of f of t dt is just f of x, right? Take the function little f, integrate it, then differentiate it. We're right back to the original function. That's the fundamental theorem of calculus part 2. And so clearly h prime of x is just going to be the derivative with respect to x of this thing, which is just g of x. So the derivative of the function h is g of x. This is the graph of the derivative. So now we're ready to answer the question. Where is h increasing? It's where its derivative is what? Positive, right? Where is the graph of g positive? When is it above the x-axis? Well, it's clearly always above the x-axis for values less than 2. So we could say from minus infinity to 2, that would be the interval notation, right? From of course, when we talk about where location, we're always talking about domain values, right? Input values along the horizontal axis here. So from negative infinity to 2, and then what? From 6 to 10, looks like we're just 0. But then from 10 to 16, we're positive again. So since it's just 0, it appears at one point, we're just going to go from 6 to 16. And then again, notice from 22 on, we're above the x-axis too. Okay, this little symbol here is the union symbol, right? In set notation, this basically means or. So we're increasing on these separate intervals. Okay, where is it decreasing? Well, now we're looking where the graph is below the x-axis because the function h is decreasing when its derivative g is negative, right? Less than 0. So we are negative less than 0 from 2 to 6. And then what from 16 to 22? What values of x do we have a local max? If you remember the first derivative test, if we have a sign change in the derivative from positive to negative, right, we can have a local maxima. Notice our critical points where the derivative is 0 are where we cross the x-axis here, right? 2, 6, 10, 16, 22. Those are critical points, but not necessarily all are extreme values. Notice that at 2, the derivative is positive to the left and then negative to the right, right? Above the x-axis to the left, below the x-axis to the right. So we change from positive to negative. So x equal 2, we have a local maximum. Where else do we change from positive to negative? Not here. Here it's positive, but then we stay positive, so there's no change in the sign of the derivative. Positive to negative at 16. So x equal 2 and x equals 16, we have local max at those two locations. Where do we have the ditto marks, right? For what values of x does h have local minima? Well, there we're looking for a sign change, what? From decreasing, so negative derivative, to what? Increasing positive derivative. So from negative to positive, we change from negative to positive at 6. Again, no change at 10. And then at 22, we change from negative to positive. So 6 and 22. And look how these agree with what we said above. Notice we're increasing, going up from negative infinity to 2, and then we're decreasing from 2 to 6. So what's happening right at 2? Increasing up to 2, decreasing after 2, up and then down. That's a local max, right? Local max. Similarly, right, we're decreasing down to 6, and then at 6 we switch over what to increasing from 6 to 16. So going down, then going up. So at 6 we have a local minima. So these are consistent, right? These are consistent. Now, where's h concave up? So remember we talked about that. H is concave up when the derivative is increasing. So where is, this is our derivative graph, where are we increasing? Well, we're increasing right here. We start going up, 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 up at x equal 4, all the way up to what? X equal 8. So from 4 to 8. And then where else are we increasing? From 10 until what? It looks like about, we'll just say about 13 and a half, just say roughly, maybe 13.4, you know, whatever, it's a guesstimation there, but we'll say 13.5, and then we're, well, I'm sorry, from 10 to 13.5, we're increasing, sorry, should be 10. And then are we, so increasing from 4 to 8, from 10 to 13 and a half, and where else are we increasing? And it looks like somewhere right around here. And we'll just say that's where it bottoms out as, close to 19, maybe 18.7 or 18.8 or 18.9, I don't know. We'll just say from 19 on. Pen is getting out of ink. So where are we concave down? We're concave down where the derivative is decreasing. Well, we're decreasing what? From minus infinity down, 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 down until we bottom out right about 4, right? So from minus infinity to 4, and then we're decreasing again from 8 to 10. And then we said this is about 13.5 all the way down to about 19. Oops. 19, sorry, making messes. Okay. So there we have our intervals. Okay, so where do we have points of inflection? You can answer that question without even looking at the graph from right here, but you know, because what we're going concave down from negative infinity to 4, and then all of a sudden from 4 to 8 we're concave up. So at 4, right, we have a change in concavity, and then from 4 to 8 we are concave up, and then 8 to 10 we're concave down. So at 8, from 8 to 10 we're concave down, 10 to 13.5 concave up. So at 10, 13.5 we change, and at 19. And basically, graphically, what are we looking at? Anytime we change what? From the derivative increasing, where we're concave up, to decreasing, or vice versa, from decreasing to increasing. So in other words, it's the location of all the extrema, local mins and maxes. Notice we have local min at 4, local max at 8, local min at 10, local max at 13.5, local min at 19. So 4, 8, 10, 13.5, and 19. Those are the points where we will have inflection points on the graph of the function h. So it's real important when you're reading these questions that you're very clear. You know, if you're given a graph, you know, are we looking for where this graph is increasing or decreasing, et cetera, or are we looking for something else, which in this case we are looking for something else, right, where this function h is increasing or decreasing. And we have to get, you know, into play here, fundamental theorem of calculus part 2. Okay, hope this helps with working on problems of this type.